Did you guys see this shit?
Is it boring driving down here with all of this? Oh my, there's a traffic jam.
You know what? When it's busy with new people constantly, it's not too bad. But when it's slow and you're by yourself, it kind of gets a little boring sometimes. Just circle.
Doesn't this look great? It's the future of transportation. Thank you, Elon. Thank you.
Going around constantly.
So is there often a lot of traffic here?
No, I think what's happening is the South Hall, the building doors are closed.
Oh, they are?
So no one's going to that. So I think what's going on is it's just these two, and that's why...
We live in such a deeply unserious country, dude. American infrastructure is literally just the Simpsons monorail episode ad infinitum. Like, that's it. There's nothing more than that, you know? Like, the whole world can be like, hey, trains work, and they can believe that for hundreds of years, okay? And then America's like, no. What if instead we built a claustrophobic, unsafe underground tunnel where cars link together like the cars of a train, except there's one driver per car in the train, and there can only be 1 to 4 people in each car of the train. And also it's not on track, so it's less efficient. And also, if anyone fucks up, everyone in there dies. And also, you can't pass anyone, and there are no, like, supplemental systems at all. And also, it can carry 1/100th of the people otherwise. And if there's a fire, you all just die. And, yeah, like, you know, like, and people bought this. People were like, yeah, dude, what if we spent $8 trillion building a single extra lane underground, except it doesn't have standard exits like a regular additional lane, and also it's unsafe, and also it costs more, and also it's claustrophobic as fuck. Dude, we get gamer tunnels. We need to look at that one Adam something video. I'm sorry, 1 second. I'll do the, then we'll do those in the thing. We'll do the thing. Just hold on. Starship Earth, it's this. Please, please, guys, please.
Oh man, there he goes again, criticizing Elon Musk. Hasn't he heard about the Wright brothers? Everybody told them that the flying machine was impossible, that humans couldn't fly like birds in the sky. And yet, despite all the odds and naysayers, they did invent the flying machine and they revolutionized our world.
Woo!
The Wright brothers were visionary geniuses. Alright, so this argument comes up over and over and over again when anyone dares to criticize one of Elon Musk's fever dreams. And it's kinda correct, in the sense that people did tell the Wright brothers that the flying machine was impossible, and that they did it anyway, and then it went on to revolutionize our world. That all sounds very nice, but what people usually leave out is that before the Wright brothers' success, hell even after it, there were dozens if not hundreds of failed ideas and just plain dumb concepts. And so bringing up the Wright brothers or any other successful inventors in defense of Elon Musk is actually an argument against Elon Musk, because it shows you that most of these ideas, most of these concepts will not work. And that
Dude, this is the fuckmobile right here. Holy shit, look at that. Get down in this thing.
most
Oh
of
my
these
god.
concepts
Fucking machine-assisted thrusting. Holy shit. Get on top of that bit. Just fucking fly. Just arms and legs out. Just let the bounce take you. God damn, that's good.
will not work, and that there will be a lot of failures before one final success.
Yeah, the bang copter.
And so let's talk about the most...
Soaking! It's a soaking assist. Shampoop, you're right. Yeah, it's a soaking assist. This was built by Mormons. You just lay on top of them. You activate the device. And it just carries you home, you know? Just takes you the rest of the way. That's cheating, dude. God can't see your soaking, but God can definitely see your soaking fuckmobile.
excruciatingly stupid idea of Elon Musk so far, Starship Earth to Earth.
No copyright. No copyright. Doesn't this literally just look like one of the endings in like a Civ game? You know what I mean? Like a Civ game, or like what was the other one? The one where all the colonists, like 6 different groups of colonists, get spread across the planet. It was like one of the really old 4X games. Alpha Centauri. Yeah. Yeah. Does feel like it. I just want to say, by the way, I know we're already in Crazy Town right now, but I love this delusional fucking reusable rocket right here. Look at this. Oh yeah, dude. Yeah, just like that. Oh, just like that, dude. No waste over here. Yep, it's just gonna do a backflip, and then it just returns to its spot. You know, it just does a little flip. Just plug it back in. That actually works. The concept works. The concept works. It's just the way they show it. So, this isn't a joke, okay? The premise is that they're going to build rocket stations on barges out in the water outside major cities, and you will go to a yacht that'll take you from the coast to the rocket, and then the rocket will go up into orbit and take you somewhere else and land on another barge.
And so what's wrong with this concept? What's wrong with the concept of strapping people to intercontinental ballistic missiles and shooting them across the planet? Well, I mean, what's not wrong with it? And so let's go through the main problems one by one. And the first problem being, of course, strapping regular people to fucking rockets. According to the official SpaceX promotional video, the max speed of this thing will be 27,000 kilometers per hour. That would be 7,500 meters per second, which also happens to be the max speed of a Falcon Heavy rocket, for example. And so, as we can see on this Falcon Heavy telemetry graph, in order to reach that top speed, the acceleration goes beyond 3 Gs. And that kind of acceleration can already cause things such as falling blood pressure, limited eyesight, muscle cramps, difficulty breathing, or blacking out. And this problem cannot be engineered away, really, because it stems from humans' biological makeup. You know, it's nice when number go big and number go up, but humans haven't evolved to be flown around in the sky at 3 Gs. You know, in contrast...
Yeah, the funny thing here is that the target audience, because a ticket on one of these rides would be like $8 billion, okay? Do you guys seriously think your average fucking, like, venture capitalist 85-year-old Murdoch tier ghoul can survive 10 seconds in that rocket at that acceleration? There's a reason why astronauts have to train. Actually, maybe this is based as fuck, dude. Elon's like, yeah, it's gonna work fine. Dude, hello, every single, you know, pharmaceutical CEO. Yes, please, right on, it's perfectly safe, you know? And then they're all just like puddles on the ground by the time they land on Epstein's Island or whatever. Wait, hold on. He might have an idea here.
A normal airplane subjects you to between 0.2 and 0.4 Gs. And even that is not recommended for people with certain medical conditions. So it's safe to assume that only physically fit, able-bodied and healthy people could take the Starship, which already excludes half of the planet's population pretty much. Well, so far things do not look good for the Starship. And with that, let's go on to problem number 2, namely that the rocket will run on fossil fuel. And so, pardon my ignorance, but why do we want to invest in fossil fuel-based transportation technology in the 21st century? So based on what I've read, a suborbital flight, which the Starship would do in case of Earth-to-Earth transportation, would require 25% of the fuel of a regular rocket flight, as in going all the way.
Sorry, I'm looking at it right now. Hold on. Positive acceleration stress. Okay, just because it's quite funny. Okay. Positive acceleration stress occurs when the direction of acceleration is along the long axis of the body from head to foot. As acceleration increases, the force exerted in the pilot from 1G to 2G, there's an awareness of increased pressure and a general feeling of heaviness in the seat, hands, and feet. 3 and 4G further increase this sensation, and movement of the extremities become difficult unless the trunk and head are supported. It might be difficult to keep them erect. The internal organs are pulled down in the body cavity, and blood pressure falls. Eyesight may become limited, or there may be total blackout. The legs may feel congested and may have muscle cramps. Breathing may become difficult. If the acceleration is uneven, or if the pilot is inexperienced, there may be mental confusion, disorientation. So this is for pilots, not for, like, rocket pilots, but I think that, like, pilots only undergo high G forces for a short period of time. But if you're in a rocket, you'd be experiencing it for a while, right? Like, if you're in a, like, in order to escape Earth's gravity in a rocket, you would have to, you would have to withstand high G acceleration forces for a pretty long time, I think, right? You only experience G's when you're accelerating? Yeah, but you have to accelerate up to, like, 15,000 meters per second or whatever, right? Yeah, it would, you'd be doing it for a little while, you know? That's why astronauts stay on their back for launch. Yeah, but you get the point, right? Like, the specifics here, I think, this would leave a lot of people at puddles, you know?
Alright, so here we have this table with the emissions to payload mass ratio, and as we can see, the Starship can haul 100 tons to low Earth orbit, and what I read in the article is that the CO2 payload column actually specifies the tonnage of CO2 emitted per ton to low Earth orbit. So that means that according to this graph, if we want to take 100 tons to low Earth orbit, that would be 2,700 tons of CO2. Now, since we're staying suborbital, we're going to apply the 25%, and so the number we get for a full Starship at suborbital flights is 675 tons of CO2. That's the approximate amount of CO2 emissions if we take these numbers to heart. And so how much does a normal airplane emit during a transatlantic flight? Well, it turns out the total emissions of an airplane between London and New York is less than 1 ton. Airplanes in general emit 90 kilograms of CO2 per hour. And so if a transatlantic flight takes, say, 8 hours, then we're looking at 720 kilograms of CO2. Meaning that if you take the Starship between New York and London, that would be an almost 1,000-fold increase in your CO2 emissions. Right, so I think I have a winning idea for Elon Musk's $100 million carbon removal competition. Don't use fucking rockets for long-distance flights. And so let's move on to problem number 3, which is noise. You know, rockets have this attribute of being really fucking loud, and so the launch pads would have to be really far from cities. According to the man himself, this would be around 20 miles away from the shore. But if you look at SpaceX's promotional video, well, the thing is right next to the city. Meanwhile, if you were really 20 miles away from the shore, you wouldn't even be able to see the skyscrapers. The coast itself disappears at 12 miles and you'll be at 20. Now 20 miles is about 32 kilometers. And let's say we have a pretty fast ferry to take all the passengers to the platform, like the MS Superfast 11. That thing has a top speed of about 50 kilometers per hour.
Super fast.
And so this ties into problem number 4, logistics. That means the ship would need around 40 minutes or so to get from the city to the platform. Now if we calculate with half an hour for the passengers to get on and off on both ends, we are looking at 1 hour and 40 minutes just to get from the harbor to the rocket. And in addition to this, you have to put 1,000 people through security. You know, 1,000 being the capacity of the Starship imagined by Elon Musk. So we can be checked.
That's cope, by the way. 1,000? 1,000 people in a suborbital rocket? No fucking way. Musk lies about his projections on every other single fucking thing he's ever invented. 1,000, that's no shot.
Charitable and say that would be...
Is it 100 and even that's aspirational? Yeah, no, it's not going to be 1,000. I'd be surprised if it was even 100. My guess, maximum would be 20 to 30.
About an hour. And then of course once you make it to the platform you would need at least half an hour to get everyone in the rocket safely and settled down, plus all the luggage would need to be loaded in and secured, and then once again this exact same procedure on the other side. And then we had the half an hour travel time because let's say we're traveling between New York and London, and would you look at that, just getting from harbor to harbor takes 6 hours and 50 minutes. Assuming there are no delays and nothing goes wrong anyway. And so how does this measure up to a regular transatlantic flight? In both cases we assume that we are already at the entrance when we begin our journey, so namely the harbor and the airport. So let's assume that if we take a regular flight, we need 1.5 hours on both ends. And so with a 7-hour 45-minute transatlantic flight, that would mean 10 hours and 45 minutes. That's 4 hours more than taking the Starship. And so have you heard about this thing called the Concorde? Its average flight time between London and New York was around 3 hours and 30 minutes. 4 hours less than a regular flight. And would you look at that, it's the same amount of time as taking the Starship, except you don't have to subject yourself to 3 Gs. Now, as we all know,
or take 1,000 times as much carbon emissions, or build an entire network of rocket barges all around the world that you have to park 30 kilometers away from shore so that the force of your rocket taking off doesn't shatter every window in the city.
The Concorde, of course, had failed for multiple reasons, but nowadays there are plans for hypersonic passenger jets. Boeing has one, for example, with a proposed maximum speed of Mach 5. This would mean that a transatlantic flight would take 2 hours. Now, it's a question whether a hypersonic flight will ever make sense due to cost and spatial limitations, but I still find it far more likely than international rocket travel. And with that, let's go over to problem number 5, the biggest one, safety. You know, rockets are somewhat difficult to build, but the concept itself is not complicated, at least not that much. I mean, you already had rockets in medieval China in the 13th century. And modern rockets, at the end of the day, aren't that complicated either. So this is what a general rocket looks like on the inside. Picture credit goes to me. As you can see, we have a fuel tank, an oxidizer tank, we have 2 pumps, pumping both the fuel and the oxidizer into the combustion chamber that produces thrust, and so rocket go fast. Now, a SpaceX thruster, namely the newest Raptor one, is a bit more complicated. It's a so-called full-flow staged combustion cycle rocket engine, pictured here. The main difference being is that instead of 2 individually powered pumps, we have 1 turbine which runs the 2 pumps both for the fuel and the oxidizer, and the turbine itself is run by fuel-rich gas from the pre-burner. So this spins the fuel and the oxidizer pumps, and then the fuel-rich gas is routed back into the combustion chamber, thus increasing efficiency. You know, previously that gas just left through an exhaust pipe and they couldn't burn it, so that's why it's a big deal that they now can. Now, believe it or not, this is actually pretty good. So congratulations to all the engineers who worked on this. However, as far as I know, this still doesn't solve the fundamental issue with rocketry. And it's the combustion chamber. Namely, how do you put together fuel and oxidizer in that little space without the rocket exploding? It's extremely tricky, but now we have it largely figured out. Rockets have indeed gotten much safer, to the point where only 1 in 100 will explode. Meaning your chances of dying are 1 in 100. Now, with airplanes, this number is 1 out of 5.4 million. That means rockets are 54,000 times more dangerous. So in order for the Starship to be as safe as airplanes, you would need to have a single rocket accident per every 5.4 million rocket flights. So what Elon Musk is proposing here is a fossil fuel-based transportation technology where passengers are subjected to 3 Gs, which will shave off 4 hours of a transatlantic flight, and all we need to do for this is make rockets 54,000 times safer. Man, what a genius, what a visionary. Not even reality or basic mathematics can stop him. You know, this actually has to be the dumbest thing that Elon...
And then, right, we get the content, I think. I can't believe this shit, man. I don't get it. Hey, guys, honest question. Yeah, you thought Spirit Airlines was bad. Honest question. I honestly don't know the answer, okay? You know how, like, the big problem with rockets is that it takes a ton of fuel to go up to break the gravity and go into orbit, but the fuel is heavy, so the more fuel you have, the more fuel you have to burn to get up there, and it's difficult to break that cycle, you know? It just keeps going up, and it's like a very thin margin. I know nuclear engines are a thing for, like, submarines and stuff. Can we get, like, a turbocharged nuclear engine that kind of does like a little bit of a nuclear bomb, but not that much? Can we do that? You know what I mean? Because like regular nuclear engines, okay, they produce a lot of energy very efficiently, but not super fast. And then nuclear bombs produce a lot of energy very fast. So we need a middle ground, okay? We need a middle ground where you're doing like a little bit of a nuclear bomb the whole time. NASA article on the idea. Ah, I'm glad NASA has taken my thoughts into consideration. 6 things you should know about nuclear thermal propulsion. More efficient than chemical rockets? Yeah, I figured that. Focused on using low enriched uranium. What pussies? Low enriched uranium. Oh my god, can you imagine? Imagine not going for the weapons grade shit, okay? I'm talking, you just get 20 pounds of enriched uranium, and you just smack that shit with a hammer, okay? I would just say fucking go for it. You know what would be super fucked up? You know how you need like a really complicated primer system and really high-grade uranium to trigger the reaction that causes an atomic explosion? How fucked up would it be if the rules of physics were just a little bit different and you didn't need super high-grade uranium? Just like regular uranium was sufficient, and you didn't need like a highly technical primer. You just needed like a strong impact. Can you imagine if like back in the dinosaur days, every once in a while a canyon just gets vaporized? You know what I mean? Because like a rock fell on a fucking uranium deposit or something. Yeah, you just need a flintstone. You have like cavemen who are like sappers or suicide bombers. They've got like a torch in one hand and like a giant glowing rock under their arm. You know, they're like, all right, the enemy tribe is that away. You know, and they just run for like 6 days straight with like wait. And the moment they see someone, they just, and then there's just a new lake there. You know, a glowing lake. That'd be good. That wouldn't be good, actually. That would be really bad for all life on Earth, I think. That would be really destructive. Excuse me. Okay, hold on. Last thing we're looking. What is it called? Fission decay work? Is it called fission decay? Is that the thing that happens when we do the thing? Nuclear decay? Okay. Nuclear decay. Stable and unstable nuclei. Types of decay. Nuclear chemistry. Crash course chemistry. Is this it? Hold on, one second.
Apparently asking if radioactive elements are always decaying into more and more stable isotopes that are eventually no longer radioactive, why are they still around at all? Fascinating question. You seem to have brought your clever pants today. Well, it's fairly simple. Given enough time, all radioactive elements would decay into non-radioactive forms. Even ultra-stable bismuth with its half-life longer than the age of the universe. But elements with short half-lives are around because they were decayed into by elements that recently decayed into them. The chain of decay from the element originally produced and whatever supernova created them to the elements that exist on Earth now last billions and billions of years. Also, I should note that some radioactive isotopes like carbon-14 in the atmosphere are constantly being renewed by cosmic rays. Now, radioactive decay occurs when a nucleus has a higher energy level than a potentially more stable version. Typically, this difference in energy is released as what's called ionizing radiation, which you know as radioactivity. It's ionizing because it has enough energy to knock electrons out or add electrons to other atoms, essentially creating ions. There are 3 general types of radioactive decay, each named for exactly what is released from the nucleus as it decays.
Alpha, beta, and gamma, right?
Let's take a look at what may be the most famous radioactive element, uranium. By far the most common naturally occurring form of uranium is the isotope uranium-238. More than 99% of the natural uranium in the world is in this form. U-238 spontaneously decays into thorium-234 in a...
That's wild. Isn't that fucked up? Reality shouldn't do that. It's like, oh, dude, look at this glowing metal that makes you sick if you're near it. Oh yeah, wait a billion years, it'll turn into a different metal. That doesn't track. Yeah, no. That doesn't track.
Process that releases something called an alpha particle. This is called alpha decay, and the particle that it emits is basically the same as a helium nucleus, 2 protons and 2 neutrons. We even describe it that way when writing it. So right away you can see that the math checks out when it comes to the protons and neutrons. 92 minus 2 is 90, and 238 minus 4 leaves you with 234. But you'll note that we don't write the charges. The helium nucleus obviously has a +2 charge, and the thorium atom would have a negative charge as well. While it's not incorrect to write them, these charges are often omitted to emphasize what's going on in the nucleus. Now, alpha particles have relatively low energy. They're pretty heavy as particles go. So while I try not to make a habit of walking around with a hunk of uranium in my pocket, alpha particles can be stopped by nothing more than a sheet of paper or cloth. The second type of radioactive decay is beta decay, which simply emits electrons. It has somewhat higher energy than alpha radiation, but it can still be stopped by aluminum foil or even the top layers of your skin. So that thorium-234 that formed when uranium underwent alpha decay, it can continue to decay on its own, and when it does, it undergoes beta decay, releasing an electron and an atom of xenon.
You're all beta
Notice
decaying.
That, again, the way we write this is a little different. Even though the thorium emits an electron, we don't use the usual symbol for electrons. Instead, we write it in nuclear notation form with the mass number at the top and the atomic number at the bottom. Since it's an electron and not a proton, we put a -1 for the atomic number. That probably seems a little bit weird right now, but next week when we talk about nuclear equations, you will see why it is useful. The third type of decay is a little different because it only emits energy, not a particle. It's called gamma decay, and it releases electromagnetic radiation similar to visible light or UV radiation, but higher on the energy scale. Because it's just energy, gamma radiation has no mass and contains no protons, neutrons, or electrons, so it's written with 2 zeros. This form of radiation is often released when electrons transition from an unstable, excited state to a more stable state that has a lower energy. That's called the ground state. Depending on how much energy the electron loses, the extra energy can be released in the form of visible or ultraviolet light, X-rays, or gamma waves. Let's take the example of nickel-60. Imagine there's an atom of nickel-60 with one or more of its electrons in an excited state. That's what the little asterisk designates. Atoms can get to this state when they are themselves the products of radioactive decay, or if they get bombarded with radiation from other reactions, pushing their electrons into a higher energy level. Now, when all those electrons drop down to the ground state, that atom is going to release some gamma radiation. But this kind of transition can also take place where other kinds of nuclear reactions.
Okay, hold on.
Hey viewers, today we will be taking a look at what critical mass is.
I want a very fancy. I want to see the thing. Spooky.
This photo has no historical value, but it's a recreation of a truly bewildering event. This man was trying to tame the devil with
Okay, I think this is gonna do it. This is gonna do it. I can feel it. This is gonna do it.
Subsequently brought upon himself
It's 4 minutes.
a truly
Chill.
horrible death.
Okay. Got kind of an odd.
To truly appreciate just how incredible this photo is, we need to understand nuclear chemistry. What's being depicted is a nuclear warhead being checked to make sure it's still ready to explode.
Cool.
Now, I shouldn't have to tell you that poking at a critical nuclear warhead with a screwdriver is a bad idea, but let's figure out just why this is such an incredible photo. Something happens when atomic nuclei become too big. They become unstable. Sure, it makes sense. Even in our world, things can only get so big. But why do nuclei have a size limit? In a nucleus, you have protons and ideally an equal number of neutrons, all smushed really close together. Now this should seem impossible, as the electrostatic repulsion from the like charges of protons should cause them to eject away from each other. But for some reason, they don't. Inside every single proton and neutron
Because of
are
positive
3
forces,
quarks
right?
binding with
Quarks.
each other through the strong force.
Yes.
Now this interaction is almost perfect, but some of the energy being shared breaks containment and stimulates the creation of mesons, which is just a quark-antiquark pair.
I didn't know that.
Mesons are then attracted themselves to specific quarks on the inside of hadrons nearby, essentially pulling them together. Then it quickly annihilates itself and the process is repeated.
Nissan.
This attraction only occurs between proton and neutron. Otherwise, the meson is repulsed by the quarks in the other hadron. This attraction is called the nucleonic force, or nuclear force. But there's another, even stronger force called spin pairing that holds nuclei together. Spin is essentially the alignment or
spinning.
direction
That's a
of the
good trick.
electrical
The
fields
whole
created
universe.
by particles. If the fields of opposite charges line up, then they can bind together. And if the fields of like charges are opposite, they can also bind. Spin pairing is just about 10 times stronger than the nucleonic force and creates a chain of pairs with this pattern all throughout the nucleus.
Holy shit, no wonder people like JoJo Part 7 so much. Jesus Christ. Steel ball run, the secret of the spin.
Now we know why protons don't just fly away. Nucleonic forces and spin pairing keep them tied together. But these forces only extend a very short distance. So when our nucleus starts to get really big, the protons out here only feel the attraction of these nearby nucleons, while feeling the repulsion of all the protons. At some point, the repulsion is stronger than the attraction, and this happens to be at lead. Elements larger than lead are no longer stable, and, given enough time, will eventually decay down to lead to lower their internal energy.
That's so fucked up. That, like, everything heavier than lead is temporary. That's super fucked up. Like, hey, just give it a few trillion years, okay? Everything bigger, everything more dense than lead. Like, what? Eventually, it'll go back to being lead, you know? This is why lead was the thing that would block Superman's X-ray, right? Because lead is the densest, stable shit, right? I don't know. No, it's not. All right, well, I'm going to believe it anyway.
So what's going on in this photo? Nuclear weapons rely on the principle that unstable atoms are, well, unstable. If left alone, plutonium-239, the material we used in older warheads, will decay into lead after a couple billion years. However, if supplied just a tiny bit more energy, in the form of a collision with a neutron, plutonium will completely split into two smaller atoms. Now this cleaving is never perfect, and on average will release 2.9 or 3 free neutrons into the environment. These neutrons then have the opportunity to split additional plutonium atoms. This chain reaction can cause nuclear explosions.
Jeez, it's like, hey, look at this. Okay, now do this several quintillion times or so.
Additional plutonium atoms.
And there you go.
This chain reaction can cause nuclear explosions.
Skadoosh.
Nuclear explosions, though, are actually rather difficult to create from these chain reactions. You need just the right parameters and conditions. If you don't trigger a fast enough chain reaction at the exact right time, you can cause a pre-detonation, which means it gets really hot, really fast, and this heat destroys the material before a substantial amount can fizzle. This will still cause a substantial thermal explosion, but you won't get the value back invested in the processes to make the fuel. Fissile material exists in 3 states: subcritical, critical, and supercritical.
That's the bad one.
These each describe the rate at which neutrons trigger additional fission. Subcritical means that for every atom that splits, it produces on average less than 1 additional fission reaction from the neutrons it releases. Supercritical means it produces more than 1, and critical means it's balanced and each fission event produces 1 more fission event. Critical mass is a parameter that describes which state a fissile material is in based on multiple variables. Basically, if you choose a value for all of these parameters, critical mass states how much of that material you would need for the neutrons released from one fission event to trigger another. So if we imagined our demon core was 5 kilograms and at critical mass, then if we change a variable to lower the critical mass, then we would have an excess of mass and thus our core would become supercritical. If we increase the critical mass, then the core would become subcritical. Both subcritical and supercritical masses affect reactivity exponentially. So if a material becomes subcritical, it will exponentially decay until it turns itself off. Alternatively,
are you following literally any of this? Because I'm not. Yeah, okay. So I think the thing is that like some types of uranium, some uranium isotopes are unstable because their cores have too many neutrons and protons packed together for the internal forces to keep them together. And that means that if they're exposed to additional energy, like they get hit with an additional like proton or whatever, it can sort of cause a cascade where it emits more, and then that hits more, and then that hits more, and that you have like billions and trillions and quadrillions and quintillions of little packed together, neutrons, sorry, not protons, packed together atoms going off all at once, and that all releases energy, and if you do that all at once, then you have a nuclear bomb. So the difficulty in creating a nuclear bomb is in enriching the uranium, right? That's the hard part. Because I imagine that building like the trigger and the primer and all the other stuff around it is, well, not easy, pretty manageable for a government, but enriching the uranium would take like a fuck ton of time and energy and stuff, and like really advanced equipment.
supercritical masses will increase exponentially until either causing a pre-detonation or having their critical mass changed by altering one of these variables. Enter Louis Slotin. Today, he's going to make sure the nuclear core, now known as the demon core, is still close to criticality.
Why?
To do this, we place a scintillation counter nearby to measure the ionizing radiation and make sure its rate consistent with criticality. In order to coax the warhead out of sleep, 2 beryllium hemispheres are placed almost around it. Beryllium acts as a neutron reflector and moderator, so that means if a neutron released from fission doesn't encounter another atom on its journey, it can reflect off the beryllium sphere back into the core and try again.
No, but that
As
makes
a result,
it dangerous.
These neutron reflectors lowers the critical mass of the core and can actually cause it to become supercritical. Normally, these 2 hemispheres are separated by 2 wedges, and this little gap right here is the only thing stopping our nuclear core from becoming supercritical, or starting an exponential nuclear chain reaction.
Wow, I hate that.
Louis Slotin, for some machismo reason, used screwdrivers instead. And as one would expect, eventually, on one occasion, while lowering the top half of the beryllium sphere, the screwdriver slipped out, causing the hemispheres to close together. This caused the sphere to become supercritical and immediately flashed Slotin's body with a lethal dose of ionizing radiation.
Oh.
The heat from supercriticality caused the reaction to slow down briefly enough to give Slotin the opportunity to flip the top half of the core onto the ground, preventing further reaction. For him, though, he was already dead. Slotin died 9 days later in agony due to acute radiation poisoning. For me, the most fascinating thing about all of this is just how much a difference this tiny little bit of space made, and how extreme the consequences are from such a small change. On top of this, it's quite mind-blowing the fact that this core was so precariously balanced at criticality.
What a fucking idiot. I'm sorry, I can't feel any sympathy. This dude is a scientist, and he's working with a fucking nuclear core. He's literally working with the most dangerous thing that exists. And he's like, yeah, dude, I'm gonna fucking bust it up. Yeah, it was a different time. OSHA didn't exist. He literally said, I'm dead right after it happened. That is so fucked, man. Jesus Christ. Apparently all he said after it happened was, well, that's that. Okay, that's Sigma. That Sigma is shit, actually. If you briefly put the bomb hat on top of the bomb ball, and then you're like, well, that's it. You know instantly. Like, yeah, okay. Too brave to live.
Just a tiny push away from something quite extreme. So remember,
He reached around to flip the two halves apart so no one else would die. I just can't believe they didn't have, like, not just wooden wedges, but like a full fucking safety thing in here. You know, like some serious equipment. What if there was some practical jokester running around the office, like, just remove the two wedges, like, whoops, here's a bomb. We're just gonna nuke this fucking office. Holy shit. That's so fucked. It was actually metal space. Yeah, I'm just saying, like, trolled. Yeah, like, holy shit, whoops, nuked the building. Jesus Christ. Here's a better video. We can't continue. I will admit I'm extremely curious right now, but we can't continue the video forever. We're already stun-locked to shit. How long was the bomb hat on the bomb? It would have, I'm guessing it would have had to be like a second or less, right? Like a really, really, really brief length of time.
His experimental protocols. In his signature pair of blue jeans and cowboy boots, Slotin would perform the
He wasn't even wearing a shirt! He was wearing sunglasses! Okay, never mind. This is Chad as fuck. This is Chad as shit. I take it all back.
criticality tests without the fail-safe spacers that would sit on the half spheres and keep it from ever completely closing. Instead, he would put his bare hand on the top half sphere and attempt to lower it using only the blade of a flathead screwdriver. That way, he could get much closer to criticality. And Slotin had successfully completed this experiment dozens of times.
I don't care. Stop.
The afternoon of the accident, Louis Slotin was conducting the same screwdriver experiment as 7 other colleagues recorded and watched. It was just like the test before, but for whatever reason, this time, the screwdriver slipped.
Because he's a human!
The spheres touched, the demon core went prompt critical. The reflected neutrons coming from the plutonium inside the sphere instantly initiated supercriticality. Like the Doglian accident, there was a flash of blue light and a wave of the dragon's heat before Slotin could flip the top half sphere off of the assembly. Naturally, the 7 other scientists in the room ran out as fast as they could as the accident occurred, but Slotin shouted them all to get back and tossed them a stick of chalk.
What?
He told them each to mark down precisely where they were standing.
Oh shit.
By establishing their positions.
Oh, that's really smart. Yeah, because that would they'd be able to math out how much radiation they were exposed to.
Relative to the demon core, Slotin would be able to calculate just how much radiation each person had just absorbed.
Calculate how dead they are.
How much their lives had just been shortened. According to physicist Raymer Schreiber, who was present in the room with Slotin that day, Slotin's first words immediately after the incident were, quote, "Well, that does it." Louis Slotin died of severe radiation poisoning 9 days later at the age of 35. He died in the same hospital as Harry Daghlian Jr. on another Tuesday the 21st as a result of the same accident with the same hunk of radioactive material. They even were cared for by the same nurse. The demonstration that day was supposed to be the final demonstration with the core before it was used in a test detonation, and it was. In those few moments,
I hope it blew
Louis
up
Slotin
good.
had been exposed to over
That bomb was infused with the souls of the lives that it had taken. It had better blow up good.
1,000 rads of radiation from the neutrons and gamma rays blasting out of the demon core. This is possibly the highest dose of radiation any human has ever taken.
Yeah?
As a comparison, 1,000 meters from ground zero in Hiroshima, the neutron radiation was measured as less than half of what Slotin had absorbed in those fractions of a second. Since 1945, over 60 criticality accidents have been recorded, leading to at least 21 deaths in facilities and labs all around the world. The flash of blue light that so often accompanies these incidents is
the fact that it literally glows is insane to me. That it's not just something they're adding on for dramatic effect. The fact that it literally, just because they put the bomb hat on, just like that, just instantly it starts glowing. If they kept the bomb hat on, would it detonate on its own, or does it need the primer to do the additional like proton injection? It would just, when it's super critical, it would just like emit a fuck ton of radiation, but it would explode. Jesus Christ. It would heat up and melt. Okay, gotcha. Heat up and melt while emitting an unimaginable amount of radiation. Okay, gotcha. Not explode.
Indication
would melt.
of the invisible radiation being released. As high-energy particles crash through the air, like these particles exiting a cyclotron, they excite the air molecules. The only way for these molecules to return to a lower energy state is to release some radiation of their own, photons of light. But while gases can absorb and re-emit the energy imparted to it by nuclear material, human bodies cannot. Instead, particles and gamma rays flying out of the nuclear cores rip electrons from the molecules that make you up and smash your cellular machinery beyond repair.
Yeah, this is the thing that's fucked up about dying of like radiation or whatever. Radiation kills you in a very different way than everything else that kills you, you know? Like fire and cold and you know, lacerations or whatever, like that all's just like, that just, you know, kills your cells. But radiation will destroy your fucking DNA composition. It doesn't just kill you, it like deletes the ability for your body to recognize what it is it should be doing to heal itself. Like it's a much more fundamental.
When enough molecular damage is done, radiation sickness can manifest itself as everything from vomiting and diarrhea to blisters, inflammation, impaired cognition, widespread organ failure, confusion, nausea, high fever, dizziness.
Yeah, it probably goes on for a while.
5 weeks
Probably
later,
does. It probably causes you to experience everything bad a body can experience, right? Like radiation damage, you know, depending on the roll of the dice, can basically just make everything bad happen. I think it's hitting you pretty. It's doing pretty much everything.
July 1st, 1946, a different nuclear core was destroyed in a 23-kiloton air-deployed nuclear weapon over Bikini Atoll. It was supposed to.
I imagine it's like the worst way to die. Oh, dude, if I was the scientist, I would have like chalked everyone's location, like done the math, and then like found the nearest like fucking guard to pull a gun out of their hands and shot myself. Yeah, 100%. Yeah. Fuck that, dude. They were in a military base, right? Doing work on that. There should have been MPs everywhere. Yeah, just fuck that. I am not sitting through 9 days of agonizing. Jesus Christ. But the data, yeah, no, I'll write down all my thoughts at the moment. You know, I'll talk to an interviewer, I'll answer their questions, and then I'll like politely request a gun, you know.
To be the end of the Demon Core. Instead, the Demon Core was melted down and redistributed throughout the rest of the United States stockpile,
I will not dignify it.
effectively getting a brand new half-life. Until next time.
That is fucking wild. Oh, we got a cute outro. Oh my god, it's like the Mystery Science Theater 3000.
Yeah. Story time with Kyle.
Hey, Hey, handsome. You look like somebody. Who do you look like? You, well, yeah, he looks like Thor, but there's like a online content creator who I'm getting vibes from. I feel like he looks like a mixture... Am I thinking of Thorin? No, Thorin is someone else. I think I'm just thinking Thorin because he looks like Thor, so I'm thinking Thorin. Doesn't he look a little bit like American Johnson? Like, non-compete? I think there are some similarities. He's got those really angular eyebrows. I always thought those looked nice. Maybe a bit like the golden one? Yeah, it's hard to say. Okay, I'm sorry. That was a very unnecessarily long stun lock, and I didn't mean for it to be that long, but I did enjoy going over that stuff.